Hey, I'm Ets, and I want to talk about converging diverging nozzles and what happens when you expand them. So converging diverging nozzles have already been discussed in class previously. When the flow comes into a nozzle, its velocity will increase until it reaches the speed of sound at the throat. Then as the flow goes through the diverging portion of the nozzle, its velocity will continue to increase. So my question was, where does the energy for this velocity increase come from? Can I show that in Fluent? So there are three main kinds of nozzles. There are underexpanded nozzles, and when the flow reaches the end, its pressure will be greater than the pressure of the atmosphere. This will cause the flow to rapidly expand as soon as it reaches the end of the nozzle. There are also ideal flows, or ideal nozzles, in which case the flow will reach the end of the nozzle, and its pressure will be equal to the atmospheric pressure. This is the most efficient form of nozzle. There are also overexpanded nozzles, so when the flow exits the throat and begins to diverge, its pressure will become less than the pressure of the atmosphere. This pressure difference will cause backflow, so the pressure and air of the atmosphere will actually push down on the flow exiting the nozzle and will cause it to form a pattern, in which case the flow begins to repeatedly reach Mach 1 and create a shock wave over and over again until it runs out of energy. So let's take a look at my model. This is my geometry. It's a very simple sort of nozzle. There's an inlet on the left, outlet on the right. It's two-dimensional. The lines in the center are used for the sake of meshing. So if we take a look at my mesh, I have two edge sizings. So on the edges, I create a large number of divisions, and then I create a face mesh so that everything between the edges would be filled in. Now if we show the mesh, you can see that it's very solid, but especially around the throat, because there are many changes taking place there. So now we can look at how I actually went about setting this up. The overextended and the underextended nozzles require different setups. Both of them required a density-based solver, but the overextended nozzle required transient, while the underextended required steady. For the models, I turned the energy on for both of them. My underextended was a laminar model, while my overextended is a K-omega SST model. My material was air, and I set it to an ideal gas. My reference values I calculated from my inlet. And then, solution methods. I used second order upwind wherever possible for the sake of accuracy. When I did a solution initialization, for my overexpanded nozzle, I used hybrid initialization. For my underexpanded nozzle, I computed from the inlet again. And then for my overexpanded nozzle, I set the time step very small, 500 time steps, 50 iterations. My underexpanded nozzle simply had the 500 iterations. So now we can look at my results. My first underexpanded nozzle is shown here. The Mach number, you can see on the right, reaches Mach 1 at the throat, and then rapidly increases. Something to take note of is that the pressure decreases as the Mach number increases. This pattern is repeated for the second underexpanded nozzle. The second underexpanded nozzle is slightly more idealized than the first by having a larger area. So the nozzle velocities between the first and second underexpanded nozzles can be compared here. The second nozzle had a slightly higher maximum velocity at the end, and it can be shown through this comparison. The most interesting nozzle was the overexpanded nozzle, in which case you can see that the pressure runs out very rapidly, as this is a grossly overexpanded nozzle. And the flow that I discussed earlier, the pattern, is immediately available to see. So the Mach 1 is reached at the throat, and then Mach 1 is reached again later on in this pattern. When you look at the nozzle velocities, you can see the streamline here on the right does not leave the center of the flow either. So from this, we can begin to gather why you cannot simply increase the area of a nozzle for as long as you wish. That is because to increase this velocity, you are essentially converting pressure energy into kinetic energy, or you're turning pressure into higher velocity.